Hello there, and welcome back to Bedtime Science. I'm really glad you're here tonight. The solar system is the only planetary system we have ever lived in, and for most of human history, it was the only one we knew existed. 8 planets, dozens of moons, millions of asteroids, billions of comets, and one middle-aged star quietly fusing hydrogen into helium at its center. A system that formed approximately 4.5 billion years ago from a rotating cloud of gas and dust and has been evolving, slowly, ever since. We know it better than any other planetary system in the universe, and yet what we have learned in the last few decades of spacecraft exploration has consistently produced surprises. Worlds that seemed simple turned out to be complex. Bodies that seemed dead turned out to be geologically active. Places that seemed barren turned out to contain the ingredients for life. The solar system, explored up close, is a far stranger and more varied place than any telescope observation from Earth could have suggested. Tonight we move through it, from the sun at the center to the farthest reaches of the Oort Cloud, through each of the planets and their extraordinary moons and the deep history of how it all came to be. Before the planets, before the moons, before the first dust grain became part of Earth, there was a cloud. It was not a cloud like the white shapes that drift through our sky, but an enormous dark molecular cloud, cold enough for atoms and molecules to remain together, rich with hydrogen, helium, and tiny grains of heavier elements forged in older stars. The iron in Earth's core, the oxygen in our water, the calcium in bones, the carbon in every living cell were not created in the young sun. They were inherited. The solar system began with recycled starlight, with material enriched by earlier generations of stars that had lived, fused heavier elements, died, and scattered their contents into space. The solar system formed approximately 4.568 billion years ago from the gravitational collapse of a molecular cloud, a cold, diffuse region of interstellar gas and dust. The collapse may have been triggered by the shockwave from a nearby supernova, which compressed the cloud beyond the critical density at which gravity overcame the internal pressure supporting it. As the cloud collapsed, it flattened into a rotating disk, the solar nebula, with a dense, hot central region that became the proto-sun material in the disk clumped together through collisions into progressively larger bodies. First microscopic dust grains stuck together electrostatically, then centimeter-sized aggregates, then meter-sized clumps, then kilometer-sized planetesimals, and eventually the planetary embryos that swept up the remaining material through their gravity. This process, called accretion, took approximately 10 to 100 million years to produce the planets in their current form. Though the timeline varied by distance from the Sun, the inner rocky planets formed faster, and the outer giant planets took longer and incorporated much more material. Planet formation was not gentle. The early solar system was a disk of collisions. Dust grains stuck together, then broke apart, then stuck again. Pebbles drifted through gas. Larger bodies swept up smaller ones. Gravity focused impacts, so the more a body grew, the better it became at growing. This produced a kind of runaway accumulation, where a few larger embryos began to dominate their local regions. The planets were not placed into finished orbits. They assembled from countless impacts, each one adding heat, changing rotation, melting rock, vaporizing ice, and sometimes knocking entire young worlds apart. The inner and outer solar system became different because temperature sorted the ingredients. Close to the young sun, only rock and metal could condense easily. Water, methane, ammonia, and other volatiles either remained gas or were driven outward. Farther from the sun, beyond the frost line, ices could survive and add mass quickly to growing planetary cores. Those icy cores became large enough to capture hydrogen and helium from the surrounding nebula before the young sun's radiation blew much of the remaining gas away. This is why the inner system is made of small rocky planets, while the outer system is ruled by giant worlds with thick envelopes and many moons. There is a hidden drama in the fact that the solar system has remained stable for billions of years. The planets are not fixed on tracks. They constantly pull on one another gravitationally. Their orbits precess, resonate, and exchange tiny amounts of energy. Over human lifetimes, this seems perfectly regular. Over millions of years, it becomes a subtle gravitational choreography. Planetary scientists can calculate the past and future with remarkable precision for long periods, but not forever, because the solar system has a chaotic component. Even a quiet planetary system is not mathematically asleep. It is balanced, but alive with motion. The Sun contains approximately 99.86% of all the mass in the solar system. Everything else, all 8 planets, all their moons, all the asteroids, all the comets, all the dust and gas of the interplanetary medium, constitutes the remaining 0.14%. The Sun is a G-type main sequence star, sometimes called a yellow dwarf, though its actual color as seen from space would appear white rather than yellow. It has a diameter of approximately 1.39 million kilometers, about 109 times the diameter of Earth, and a mass of approximately 2 times 10 to the power of 30 kilograms. At the Sun's core, where temperatures reach approximately 15 million degrees Celsius and pressures approximately 250 billion times Earth's atmospheric pressure, hydrogen nuclei fuse to form helium through the proton-proton chain reaction, releasing energy that takes approximately 100,000 years to work its way from the core to the surface before escaping as the light and heat that sustain life on Earth. The Sun has been burning for approximately 4.6 billion years and has enough hydrogen fuel remaining for approximately another 5 billion years. The scale of the Sun is difficult to hold in the mind because it is both familiar and almost impossible. It rises every morning so predictably that it can feel ordinary, but every second it converts roughly 4 million tons of mass into energy. That energy leaves the core as gamma rays, scatters through the dense radiative zone, rises through the convective zone in enormous cells of plasma, and finally escapes the photosphere as visible light. A photon that reaches your window tonight may have spent tens of thousands of years wandering inside the Sun and just over 8 minutes crossing the empty distance to Earth. The surface of the Sun is not a solid surface. It is a visible layer of plasma, about 5,500 degrees Celsius, textured by granules that are each roughly the size of countries on Earth. Beneath that restless surface, hot plasma rises, cools, sinks, and rises again, making the Sun a boiling star rather than a glowing ball of fire. Fire requires oxygen and chemical combustion. The Sun is not burning in that ordinary sense. It is shining because gravity has compressed its core so intensely that atomic nuclei fuse, turning hydrogen into helium and releasing the energy that holds the solar system in light. The Sun also has moods. Its magnetic field twists, stores energy, and sometimes releases it violently as solar flares and coronal mass ejections. The Sun follows an activity cycle of roughly 11 years, during which sunspots, flares, and magnetic storms rise and fall. To Earth, these storms can produce auroras, interfere with satellites, disturb radio communication, and induce currents in power grids. The same star that makes life possible also sends weather through space. The solar system is not a still arrangement of planets. It is immersed in the breath of the Sun. The word planet comes from an ancient word meaning wanderer, because planets were first known not as worlds, but as lights that moved against the background of fixed stars. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye long before anyone knew what they were. They were omens, gods, markers of time, navigational companions, and puzzles in the sky. Only much later did telescopes reveal that these wandering points were not lights painted on a sphere, but worlds, each with its own weather, gravity, surface, moons, or atmosphere. The solar system is therefore also a story of human perception widening, step by step, from myth to measurement. Mercury is the smallest planet in the solar system and the one closest to the Sun, orbiting at an average distance of approximately 57.9 million kilometers. Its orbit is the most elliptical of any planet in the solar system, varying between about 46 million kilometers at closest approach and 70 million kilometers at greatest distance, which produces significant variation in the amount of solar energy it receives over the course of its 88-day orbit. Despite being the closest planet to the Sun, Mercury is not the hottest. That distinction belongs to Venus. The reason is that Mercury has virtually no atmosphere to trap heat, so its surface temperature swings wildly between approximately 430 degrees Celsius on the sunlit side and minus 180 degrees Celsius on the night side. Mercury is remarkably dense, the second densest planet after Earth, suggesting an unusually large iron core that constitutes approximately 85% of the planet's radius. The leading explanation is that a giant impact early in solar system history stripped away much of Mercury's rocky mantle, leaving the iron-rich interior disproportionately exposed. Mercury is covered with impact craters, ancient volcanic plains, and a unique tectonic feature: enormous scarps, cliff-like formations, hundreds of kilometers long and up to 3 kilometers tall that formed when the planet's iron core cooled and contracted, shrinking the planet and wrinkling its surface like a drying grape. The Caloris Basin, one of the largest impact craters in the solar system, was formed approximately 3.9 billion years ago when a large asteroid struck Mercury with such force that the shock waves focused through the planet's interior and disrupted the terrain on the opposite side of the planet, the so-called antipodal terrain, a chaotic region of disrupted hills and valleys that formed when seismic energy converged at the exact point diametrically opposite the impact site. NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, discovered water ice and organic compounds in permanently shadowed craters near Mercury's poles, regions that never receive direct sunlight and are cold enough to preserve ice despite the planet's general proximity to the Sun. Mercury feels at first like a simple world, small, scorched, cratered, and airless. Yet its simplicity disappears when studied closely. Its surface preserves a violent early history, but it also shows signs that volatile substances once existed there in quantities no one expected. Messenger's discovery of polar ice was surprising because Mercury is so close to the Sun, but the geometry of its poles creates permanent shadow. Inside those craters, sunlight never reaches the floor. A world that can reach oven-like heat at noon can also hold ancient ice and darkness. Mercury's orbit helped change physics. For centuries, astronomers noticed that the planet's perihelion, the closest point in its orbit to the Sun, shifted slightly more than Newtonian gravity could explain. The difference was tiny, but persistent. In 1915, Einstein's general theory of relativity explained the anomaly by showing that the Sun's mass curves space-time and alters Mercury's orbit. In this way, the smallest planet became one of the first great tests of a new understanding of gravity. Mercury is not only a cratered rock near the Sun, it is part of the history of how humans learned that space and time are not separate, rigid things. Venus is almost exactly Earth's twin in size and mass, approximately 95% of Earth's diameter and 81% of Earth's mass, and yet it is one of the most hostile environments in the inner solar system. Its surface temperature averages approximately 465 degrees Celsius, hotter than Mercury despite being nearly twice as far from the Sun, because its dense atmosphere of carbon dioxide and clouds of sulfuric acid produce an extreme greenhouse effect that traps virtually all the solar energy absorbed by the surface. The atmospheric pressure at Venus's surface is approximately 92 times Earth's atmospheric pressure, equivalent to the pressure at approximately 900 meters depth in Earth's oceans. The Soviet Venera landers that reached the Venusian surface between 1970 and 1982 survived for only 23 to 127 minutes before being crushed and incinerated by the hostile environment, long enough to transmit the first images and measurements from another planet's surface. Venus also rotates backwards relative to most planets and relative to its orbit, and so slowly that a Venusian day, one full rotation, takes approximately 243 Earth days, longer than a Venusian year of 225 Earth days. Venus is one of the most haunting comparisons in planetary science because it shows how two worlds can begin with similar size and end in profoundly different states. Earth and Venus are nearly twins in bulk properties, but one became blue and habitable while the other became a pressure cooker beneath sulfuric acid clouds. Venus reminds us that habitability is not simply a matter of size or distance. It is a system-level outcome involving atmosphere, water, volcanism, rotation, clouds, geochemistry, and time. The sky of Venus would not look open from the surface. It would be a thick orange haze, lit by sunlight filtered through layers of cloud. The surface would be dim, hot, and still in the lower atmosphere, with a pressure that feels more like deep ocean than open air. Yet high above the surface, in the cloud layers, temperatures and pressures become far more Earth-like. This has led some researchers to consider the clouds of Venus as a possible astrobiological environment, though the acidity is extreme and the evidence for life is not established. Venus teaches caution. An interesting possibility is not a discovery, and planetary science must hold wonder and skepticism together. Venus also rotates so slowly that its surface day is stranger than almost any calendar on Earth. Because the planet spins backward and slowly, the sun would rise in the west and set in the east, and a solar day on Venus lasts about 117 Earth days. Time itself, on Venus, would feel heavy. Noon would come after weeks. Night would last for weeks. Beneath the clouds, the planet turns with an almost unbearable patience. The surface of Venus, radar mapped in detail by the Magellan spacecraft between 1990 and 1994, is a landscape of volcanic plains, highland plateaus, and numerous volcanoes, some of which may still be active. Recent analysis of Magellan data published in 2023 found evidence of a volcanic vent that changed shape over an 8-month period, suggesting active volcanism on Venus for the first time with direct observational support. Venus has no magnetic field and no moons, and its lack of plate tectonics appears to mean that heat escaping from its interior cannot do so gradually through seafloor spreading as on Earth, but instead may do so episodically through catastrophic resurfacing events in which the entire crust is overturned. The relative youth of Venus's surface, many broad volcanic plains and tectonic features appear geologically young by planetary standards, often discussed in the range of hundreds of millions of years, is consistent with such a resurfacing event having occurred geologically recently in the planet's history. Earth is ordinary only because we are inside it. From the perspective of planetary science, it is astonishing. It has long-lived oceans, plate tectonics, oxygen made by life, continents that rise above water, an atmosphere thin enough to see through and thick enough to protect the surface, and a biosphere that has altered the chemistry of the entire planet. Earth is not simply a planet with life on it. It is a planet changed by life. The oxygen in the air, the limestone in cliffs, the soils beneath forests, even the red beds in ancient rocks, are records of biology participating in geology. The Earth system is held in balance by feedbacks that are not perfect but are powerful. The carbon-silicate cycle, driven by weathering, volcanism, oceans, and plate tectonics, has helped regulate climate across geological time. When carbon dioxide rises, warmer temperatures and increased weathering can draw some of it down into minerals and sediments. When carbon dioxide falls, volcanism can replenish it. This feedback operates over very long timescales, much too slowly to protect human civilization from rapid climate change. But over hundreds of thousands to millions of years, it has helped keep Earth within a range where liquid water could persist. Earth's magnetic field is another hidden protection. Generated by the motion of molten iron alloys in the outer core, it extends into space and forms a magnetosphere that diverts much of the solar wind. It does not make Earth invulnerable, and it is not the only reason the atmosphere survives, but it is part of the planetary shelter under which life has developed. Every aurora is a visible reminder of that invisible shield, charged particles guided by magnetic fields into polar skies, making curtains of green and red light at the edge of space. Earth is the only known world in the universe with confirmed life, with liquid water oceans covering approximately 71% of its surface, and with a thin biosphere extending from the deep ocean floor to approximately 15 kilometers altitude in the atmosphere. Earth's position in the habitable zone of the Sun, the range of distances at which liquid water can exist on a planetary surface, combined with its moderately sized mass retaining an atmosphere, its active plate tectonics recycling carbon and maintaining a long-term climate buffer, its large moon stabilizing its axial tilt, and its strong magnetic field protecting it from solar wind erosion of the atmosphere, are among the factors that have allowed complex life to persist and diversify over approximately 3.7 to 4 billion years. Whether all these factors are necessary for life, or whether life can emerge and persist under much more varied conditions, is one of the central questions of astrobiology, a field whose answer has profound implications for the likelihood of life elsewhere in the universe. The Moon is often treated as a companion object, but it is also one of the most important archives in the solar system. Earth constantly erases its own surface through weathering, erosion, volcanism, and plate tectonics. The Moon, by contrast, preserves impact scars from billions of years ago. Its surface is a museum of bombardment. The dark maria, visible with the naked eye, are ancient lava plains that filled large impact basins. The bright highlands are older, more heavily cratered terrain. When astronauts walked on the Moon, they were walking on a surface that keeps time differently from Earth. The Moon also shapes life in ways that feel ordinary because they are constant. Its gravity raises tides, which have influenced coastal ecosystems, navigation, and possibly early environments where chemical cycles were concentrated by wetting and drying. Tidal interactions are also slowing Earth's rotation very gradually. The day was shorter in the deep past. Ancient tidal rhythmites suggest that hundreds of millions of years ago, Earth's day may have been closer to 22 hours. The Moon is moving away, and Earth is slowing down, both bodies exchanging angular momentum in a slow gravitational conversation that has lasted since the giant impact. There is something unusually intimate about the Moon compared with the rest of the solar system. It is close enough that light takes only about 1.3 seconds to cross the distance. It is the only world beyond Earth where human beings have stood. It is also the only celestial body whose face has watched every human culture. Before maps, before writing, before agriculture, people looked up and saw the same lunar phases. The Moon is science, but it is also memory. The Moon formed approximately 4.5 billion years ago from the debris ejected when a Mars-sized body, named Theia by planetary scientists, collided with the early Earth in what may have been the most violent event in Earth's history. The giant impact hypothesis, now the dominant model for lunar origin, explains why the Moon is relatively large compared to Earth, why its composition is similar to Earth's mantle, why it has no iron core comparable to Earth's, and why the Earth-Moon system has the angular momentum it does. The Moon is the fifth largest moon in the solar system and the largest relative to its parent planet. Its gravitational influence stabilizes Earth's axial tilt. Without the Moon, Earth's axis would wobble chaotically over geological time, producing dramatic swings in climate that might have prevented the stable long-term conditions needed for complex life to evolve. The Moon is also slowly moving away from Earth at approximately 3.8 centimeters per year, receding as the tidal interaction between Earth's oceans and the Moon transfers angular momentum from Earth's rotation to the Moon's orbit. Mars holds attention because it is neither completely alien nor remotely habitable in its present state. Its sky can be pinkish or butterscotch. Its sunsets can appear blue because fine dust scatters light differently from Earth's atmosphere. Its surface preserves river deltas, ancient lake beds, mineral veins, and clay-rich rocks that formed in water. Rovers have driven through landscapes that seem almost familiar: dry valleys, layered sediments, dunes, weathered stones, but under a sky too thin to breathe and a radiation environment too harsh for unprotected life at the surface. Mars is the most explored planet beyond Earth, with numerous spacecraft in orbit and multiple rovers and landers on its surface. It is a cold, dry desert world with a thin carbon dioxide atmosphere approximately 1% the density of Earth's, surface temperatures ranging from approximately minus 125 degrees Celsius at the poles in winter to approximately 20 degrees Celsius near the equator in summer, and a landscape dominated by ancient impact craters, volcanic plains, enormous extinct volcanoes, and a vast canyon system. Olympus Mons, the largest volcano in the solar system, rises approximately 22 kilometers above the surrounding plain, nearly 3 times the height of Everest above sea level, and has a base diameter of approximately 600 kilometers, so large that an observer standing at its center would not be able to see its edges over the horizon. Valles Marineris, the canyon system stretching approximately 4,000 kilometers along Mars's equator, is large enough to span the continental United States from coast to coast, and in places reaches depths of approximately 7 kilometers. Mars also has seasons, dust storms, polar caps, and weather. Its atmosphere is thin, but it is not absent. Dust can rise and sometimes spread globally, covering the planet in a veil that changes temperature and sunlight. Carbon dioxide frost forms and sublimates at the poles. Water ice lies beneath the surface in many regions. Mars is not dead in the simple sense. It is active in its own cold, quiet way, with winds moving dust across crater floors and carbon dioxide changing phase with the seasons. The question of life on Mars has changed over time. In the 19th century, some observers imagined canals and civilizations. In the 20th century, spacecraft revealed a dry, cold world, and expectations became more modest. Today, the question is careful and scientific. Did microbial life ever arise when Mars was warmer and wetter? And if it did, could chemical traces or fossil biosignatures remain in ancient rocks? That is why sample return matters so much. Instruments on a rover can do remarkable work, but laboratories on Earth can examine tiny structures and chemical patterns with far greater precision. Mars has extensive evidence of ancient water activity, dried river valleys, lake beds, and minerals formed in the presence of liquid water, indicating that the planet was warmer and wetter billions of years ago. The leading hypothesis is that Mars lost most of its atmosphere and water when it lost its global magnetic field approximately 4 billion years ago, after which the solar wind gradually stripped the atmosphere away. Mars currently has 2 small moons, Phobos and Deimos, which are thought to be captured asteroids. Phobos orbits so close to Mars, approximately 6,000 kilometers above the surface, that tidal forces are gradually drawing it closer, and it is expected to either break apart into a ring system or crash into Mars in approximately 50 million years. The Perseverance rover, which landed in Jezero crater in 2021, is collecting samples from what was once an ancient lake environment in the hope that they will eventually be returned to Earth and analyzed for signs of ancient microbial life. The asteroid belt is often imagined incorrectly as a crowded field of tumbling rocks. In reality, it is mostly empty space, and that emptiness is part of its beauty. The asteroids are not packed together like stones in a riverbed. They are separated by enormous distances, each one following its own orbit around the Sun. A spacecraft can pass through the belt with little risk because space remains overwhelmingly larger than matter. The asteroid belt, located between the orbits of Mars and Jupiter, contains millions of rocky and metallic objects ranging in size from tiny pebbles to the dwarf planet Ceres, which has a diameter of approximately 945 kilometers and contains approximately 1/3 of the total mass of the entire asteroid belt. Despite the density of objects depicted in science fiction films, the asteroid belt is in reality extraordinarily empty. Spacecraft have flown through it multiple times without any risk of collision because the average distance between objects is several 100,000 kilometers. The total mass of everything in the asteroid belt is approximately 4% of the mass of the Moon. The asteroids are the remnants of the early solar system, material that never coalesced into a planet, primarily because Jupiter's powerful gravity perturbed the orbits of objects in the region, preventing them from accreting efficiently. The composition of asteroids varies with distance from the Sun. The inner belt is dominated by rocky, silicate-rich S-type asteroids, while the outer belt contains darker, more primitive C-type asteroids rich in carbon and volatiles. Yet the asteroids are scientifically rich because they are leftovers. Some are fragments of differentiated bodies that once melted, separated into cores and mantles, and were later shattered. Others are primitive, carbon-rich objects that preserve early solar system chemistry. The asteroid Vesta, visited by NASA's Dawn mission, is large enough to have a basaltic crust like a small planet. Ceres, also visited by Dawn, contains water-bearing minerals and bright salt deposits in a crater, suggesting brines once moved through its interior. The asteroid belt is therefore not one thing. It is a library of failed planets, broken worlds, and preserved ingredients. Meteorites that fall to Earth give us pieces of that library in our hands. Some contain chondrules, tiny once molten droplets that formed in the solar nebula. Some contain calcium, aluminum-rich inclusions, among the oldest dated solids in the solar system. Some contain amino acids and organic molecules, showing that complex chemistry was present before planets finished forming. A meteorite on a museum table may look like a dark stone, but it can be older than Earth itself. Jupiter is often called a planet, but in scale and influence, it is almost a system of its own. Its magnetosphere is enormous, stretching millions of kilometers, large enough that if it were visible from Earth, it would appear bigger than the full Moon. Its radiation belts are intense. Its gravity shapes asteroid families, comet paths, and resonances across the solar system. Jupiter is not merely one planet among 8. It is the dominant gravitational presence after the Sun. Jupiter is the largest planet in the solar system, with a mass approximately 318 times that of Earth and a diameter approximately 11 times Earth's. It is a gas giant with no solid surface, its atmosphere consisting primarily of hydrogen and helium that gradually becomes denser with depth until ordinary ideas of gas and liquid begin to blur. As of the 2026 announcements from the International Astronomical Union's Minor Planet Center, Jupiter has 101 known moons, second only to Saturn's much larger confirmed moon family. Many of Jupiter's smaller moons are distant, irregular bodies, probably captured asteroids or fragments from old collisions. But the 4 Galilean moons remain the heart of the system, large enough to be worlds in their own right, and different enough from one another to feel like 4 separate experiments in planetary evolution. Inside Jupiter, pressure changes matter into forms that do not exist naturally on Earth at ordinary conditions. Hydrogen, the lightest element, becomes a conducting metallic fluid deep within the planet. This metallic hydrogen, stirred by rotation and convection, helps generate Jupiter's powerful magnetic field. There may be no solid surface to stand on. Instead, a descent into Jupiter would be a descent through thicker and thicker atmosphere, through clouds of ammonia, ammonium hydrosulfide, water, and eventually into regions where gas and liquid distinctions blur under crushing pressure. The Great Red Spot is famous, but Jupiter's entire atmosphere is a masterpiece of fluid dynamics. Bright zones and dark belts move in opposite directions. Storms merge, shrink, fade, and reappear. Lightning flashes in deep water clouds. At the poles, Juno revealed clusters of cyclones arranged in geometric patterns, as if the planet's weather had found a kind of rotating order. Jupiter is not still. It is a giant weather engine, turning faster than any other planet, completing a day in just under 10 hours. The Galilean moons make Jupiter feel like a miniature solar system. Io is a world of fire, Europa a world of ice and ocean, Ganymede a magnetic world larger than Mercury, and Callisto an ancient cratered archive. For moons, for radically different outcomes, all orbiting the same planet. Their diversity comes from distance, composition, tidal heating, and history. Io, closest to Jupiter, is needed by gravity until its interior melts. Europa, farther out, receives enough tidal energy to keep an ocean liquid beneath its ice. Callisto, farther still, remained comparatively less processed, holding ancient scars. Europa is especially compelling because it combines 3 ingredients astrobiologists care about: liquid water, chemistry, and energy. Its surface is young, cracked, and possibly connected to the ocean below. If material from the ocean sometimes reaches the surface, a spacecraft might study ocean chemistry without drilling through kilometers of ice. NASA's Europa Clipper mission, launched in the 2020s, is designed to make repeated flybys of Europa, mapping the ice shell, measuring the magnetic and gravity fields, and studying whether the moon has conditions suitable for life. It is not a life detection mission in the strictest sense, but it is a habitability mission of enormous importance. Ganymede, too, is more than a large moon. Its magnetic field implies a differentiated interior, and evidence suggests it may contain layers of ocean and ice deep below the surface. Callisto may also harbor a subsurface ocean, though its geology appears far older and less active. The outer solar system changed the definition of an ocean world. Oceans are not only blue surfaces under sunlight. They can be hidden under ice, in darkness, kept liquid by tidal heat, radiogenic warmth, or salts that lower freezing points. Ganymede and Callisto complete the Galilean pattern in quieter ways. Ganymede is the largest moon in the solar system, larger than Mercury, and the only moon known to generate its own intrinsic magnetic field. Callisto is an ancient archive, heavily cratered and comparatively less altered than Io or Europa. It may also hide a deep ocean, but its surface does not advertise that possibility with the same youthful cracks that make Europa so visually dramatic. In the Jupiter system, a single planet holds volcanic fire, hidden water, magnetic complexity, and ancient stillness all at once. The Galilean moons also created a revolution in human thought. When Galileo saw 4 points of light changing position around Jupiter in 1610, he had direct evidence that not everything revolved around Earth. The observation did not by itself prove the full heliocentric model, but it weakened the old assumption that Earth was the center of all motion. A few small moons, seen through an early telescope, helped open the universe. Sometimes a philosophical shift begins with dots of light in the wrong place. Saturn's rings are one of the most beautiful structures humans have ever seen, but they are also a temporary structure. They are bright because they are mostly clean water ice, and that brightness suggests youth or constant renewal. Cassini measurements indicated that material from the rings is slowly falling into Saturn, a process sometimes called ring rain. The rings may not last forever. A future solar system, seen hundreds of millions of years from now, might have a Saturn with much fainter rings or none like the ones we know. The rings are not a single solid disk. They are countless particles, each orbiting Saturn independently, from dust grains to icy boulders. Gaps, waves, scalloped edges, and braided structures are sculpted by the gravity of small moons. Tiny moonlets create propeller-shaped disturbances. The Cassini division, visible in telescopes from Earth, is maintained by orbital resonance with the moon Mimas. Saturn's rings are therefore a visible laboratory of orbital mechanics, gravity writing patterns into ice. Saturn itself is gentle looking from a distance, with pale gold bands and soft colors, but its atmosphere is dynamic. It has storms, jet streams, lightning, and a persistent hexagonal wave pattern around its north pole, a six-sided structure larger than Earth. The hexagon is not a solid object, but a standing atmospheric wave shaped by rotation and flow. It is one of those solar system features that sounds almost invented until spacecraft images make it undeniable. Saturn is the second largest planet, a pale giant surrounded by the brightest rings and, as of current counts, the largest confirmed family of moons of any planet. Modern surveys and 2026 confirmations from the International Astronomical Union's Minor Planet Center have brought Saturn's moon count to 285, most of them small and faint, and the number may continue to change as deeper surveys improve. Cassini transformed the best-known moons into worlds with personalities: Titan with weather and lakes, Enceladus with plumes from a hidden sea, Iapetus with its dark and bright hemispheres, and Mimas with a crater so large it makes the moon look almost unreal. Saturn is therefore not only a ringed planet. It is an entire outer solar system neighborhood. Enceladus is powerful because it lets the hidden ocean speak. Europa keeps its ocean sealed under ice, at least most of the time. Enceladus throws pieces of its ocean into space. Cassini did not need to drill, melt, or land. It flew through the plumes and sampled them with instruments. The result was one of the most extraordinary astrobiological discoveries of the modern era: a small moon, barely more than 500 kilometers wide, venting salty water, organic compounds, and molecular hydrogen from an ocean in contact with rock. The presence of molecular hydrogen matters because on Earth, hydrogen can feed microbial ecosystems near hydrothermal vents. It is not proof of life. It is proof of an energy source that life could use. Later analyses of Cassini data have also found additional organic molecules in fresh plume particles, strengthening the case that Enceladus contains the ingredients for complex chemistry. But the careful sentence remains the most important one. Enceladus is not known to be inhabited. It is known to have an ocean, organics, and chemical energy. Titan is strange in a different way. It is cold beyond ordinary imagination, about -179 degrees Celsius at the surface, yet it has weather, lakes, dunes, clouds, and rain. The rain is methane. The rivers are methane and ethane. water ice behaves almost like rock. Organic haze fills the atmosphere, making Titan's sky orange and opaque. It is the only place besides Earth known to have stable liquid on its surface, but the liquid belongs to a different chemistry. Titan may also have a subsurface water ocean beneath its icy crust, meaning it could hold two kinds of interesting environments: a surface where organic chemistry occurs in methane and ethane, and an interior where liquid water may exist. NASA's Dragonfly mission, planned as a rotorcraft lander, is intended to explore Titan's surface by flying from place to place, studying chemistry in dunes and possible impact melt regions. The idea of a flying laboratory on a moon of Saturn would have sounded like fantasy not long ago. Now it is a mission architecture. The Huygens probe's descent through Titan's atmosphere remains one of the most dreamlike moments in space exploration. It fell beneath orange haze, photographed channels carved by liquid hydrocarbons, and landed on a surface scattered with rounded water ice pebbles. For a short time, a human-built machine sat on the surface of a moon in the outer solar system, listening to a world no one had seen from the ground before. The rings of the giant planets are not all like Saturn's. Jupiter has faint dusty rings, discovered by Voyager 1, fed partly by material knocked from small inner moons. Uranus has dark, narrow rings, discovered in 1977 when they blocked starlight before and after the planet itself passed in front of a star. Neptune has faint rings and clumpy arcs whose persistence once puzzled scientists. Ring systems are common around giant planets, but Saturn's are unusually bright, broad, and spectacular. The difference is not whether rings exist. It is how visible and massive they are. The boundary between moon and ring can be fluid over time. A moon can be broken into rings if it passes within a planet's Roche limit, where tidal forces exceed its self-gravity. Ring material can clump into moonlets. Moons can shepherd rings, confining their edges with gravitational tugs. Saturn's system shows these interactions beautifully, but the same principles apply elsewhere. The solar system is full of transitions: dust to rock, rock to planetesimal, moon to ring, ring to moon. Uranus is the seventh planet from the Sun and the first to be discovered with a telescope, identified as a planet by William Herschel in 1781. It is an ice giant, a category distinct from the gas giants Jupiter and Saturn, with a bulk composition dominated by ices including water, ammonia, and methane beneath a hydrogen and helium atmosphere. The most striking feature of Uranus is its extreme axial tilt. The planet rotates on its side, with its axis of rotation tilted approximately 98 degrees relative to its orbital plane. This means that during each pole summer, the sun is nearly directly overhead, and during winter, a pole is in continuous darkness for approximately 42 years. The cause of this extreme tilt is thought to be a giant impact early in the solar system's history. Uranus also has the coldest atmosphere of any planet, reaching approximately -224 degrees Celsius, colder than even more distant Neptune, a mystery related to the fact that Uranus, unlike all the other giant planets, does not appear to radiate significantly more heat than it receives from the Sun. Uranus is a reminder of how much we still do not know even about our own neighborhood. Voyager 2 passed it once, in 1986, during a southern summer when one pole faced the Sun. That flyby gave humanity almost everything it knows from close range about the Uranian system, yet it was brief. We have never orbited Uranus. We have never watched its seasons unfold from nearby. We have not mapped its moons in detail. A whole planetary system remains known mostly from a few days of encounter data and decades of distant telescope observations. The sideways tilt of Uranus creates some of the strangest seasons in the solar system. Imagine a planet where one hemisphere can face decades of daylight while the other sits in decades of darkness. The atmosphere responds slowly, And because Uranus receives so little sunlight, seasonal changes unfold with unusual patience. The planet appears calm in many images, a pale blue-green sphere, but later observations from Hubble and large ground-based telescopes have shown storms and cloud activity. Uranus may look quiet because we have not watched it closely enough. The moons of Uranus are also underappreciated. Miranda's patched terrain looks as if pieces of different moons were assembled together, with enormous fault scarps and oval regions called coronae. Ariel may have been resurfaced by cryovolcanic or tectonic activity. Titania and Oberon may contain internal oceans if enough heat and antifreeze compounds are present. The Uranian system may turn out to be far more geologically and astrobiologically interesting than its brief Voyager portrait suggested. Uranus has 13 known rings, all much darker and narrower than Saturn's rings, and 28 confirmed moons, all named after characters from the works of William Shakespeare and Alexander Pope. Its moons show remarkable geological diversity. Miranda, the smallest of the 5 major Uranian moons, has one of the most dramatic landscapes in the solar system, with a cliff called Verona Rupes approximately 20 kilometers tall. If you fell off it in Miranda's low gravity, it would take approximately 12 minutes to hit the bottom. Ariel shows extensive canyon systems and geological activity. Titania and Oberon, the largest Uranian moons, show ancient, heavily cratered terrain. The extremely limited data from Uranus, only one spacecraft, Voyager 2, has ever visited it, flying past in 1986, means that many aspects of the Uranian system remain poorly characterized. Neptune is the 8th and outermost planet, with a diameter approximately 4 times Earth's and a mass approximately 17 times Earth's. Like Uranus, it is an ice giant. It was discovered in 1846 through mathematical prediction. Observations of anomalies in Uranus's orbit allowed astronomers Urbain Le Verrier and John Adams independently to calculate where an undiscovered planet must be located, and when telescope observations were made at that position, Neptune was found essentially exactly where the mathematics said it should be. This triumph of Newtonian mechanics confirmed the predictive power of gravitational theory. Neptune has the most extreme winds in the solar system, with speeds of approximately 2,100 kilometers per hour, supersonic. The Great Dark Spot, a storm system observed by Voyager 2 in 1989, had disappeared by the time the Hubble Space Telescope observed Neptune in 1994, suggesting that Neptune's atmosphere changes on relatively short timescales. Neptune radiates approximately 2.6 times as much energy as it receives from the Sun, indicating significant internal heat production. Neptune was found by mathematics before it was understood by sight, and that gives it a special place in astronomy. Its discovery showed that gravity could reveal an unseen world. A planet had tugged on Uranus just enough to leave a pattern in its motion, and the pattern pointed to Neptune. This is one of the quietest kinds of discovery. Not a sudden bright object, not a dramatic explosion, but a discrepancy followed to its source. Neptune's blue color comes largely from methane-absorbing red light, though the exact reason it is a deeper blue than Uranus remains an active subject of atmospheric study. Its winds are astonishing, especially because the planet receives so little sunlight. Internal heat must help power its weather, but the details of how an ice giant atmosphere organizes energy remain incomplete. Neptune is therefore both remote and meteorologically alive, a cold world with some of the fastest winds known. Triton may be a captured dwarf planet, and that origin changed everything. If Neptune captured Triton, the event would have disrupted any earlier moon system, sending existing moons into new orbits or destroying them. Triton's surface, seen by Voyager 2, is young in places, with cantaloupe-like terrain, nitrogen frost, and dark streaks from geysers. Because Triton is similar in many ways to Pluto but altered by Neptune's gravity, it may be one of the best natural bridges between the planetary region and the Kuiper Belt. Neptune's largest moon, Triton, is one of the most unusual objects in the solar system. It is the only large moon in the solar system that orbits its parent planet in the retrograde direction, opposite to the planet's rotation, which is strong evidence that Triton is a captured object rather than a moon that formed alongside Neptune. The most likely origin is that Triton was originally a large Kuiper Belt object that was captured by Neptune's gravity in the early solar system. Triton is geologically active. Voyager 2 observed geysers of nitrogen gas erupting from its surface, driven by the sublimation of nitrogen ice heated by sunlight. Triton's retrograde orbit is slowly decaying due to tidal interaction with Neptune, and in approximately 3.6 billion years, Triton will either break apart into a ring system or impact Neptune. Triton has a thin atmosphere of nitrogen and shows evidence of seasonal changes, with its south polar region covered by a bright nitrogen ice cap that extends and retreats with the extremely long Neptunian seasons. The Kuiper Belt changed the solar system culturally as well as scientifically. For much of the 20th century, Pluto seemed lonely, a small ninth planet at the edge. Then telescopes began finding other icy bodies beyond Neptune. Some small, some large, some in resonances, some with moons, some with strange shapes and rapid rotations. Pluto was no longer an exception. It was a member of a population. The edge of the solar system became richer, and the old list of planets became less adequate to describe what was really there. New horizons transformed Pluto from a point of light into a world. Sputnik Planitia, the bright heart-shaped basin, is a plain of nitrogen ice that appears geologically active, with convection cells slowly turning over like a frozen lava lamp. Mountains made of water ice rise along its margins because at Pluto's temperature, water ice is hard enough to behave like rock. There are possible cryovolcanic structures, hazes in the thin atmosphere, dark reddish regions colored by complex organic molecules called tholins, and a system of small moons whose rotations are chaotic. Pluto did not become less wonderful when it became a dwarf planet. It became more understandable. Arrokoth, the Kuiper Belt object visited by New Horizons in 2019, revealed something even more ancient. It is a contact binary, two lobes gently joined, likely formed by slow accretion in the early solar system rather than violent collision. Its flattened, reddish form suggests that some outer solar system bodies preserve the original low-speed assembly of planetesimals. Arrokoth is small, but it may be one of the most pristine objects ever visited by a spacecraft, a relic of the time before planets finished forming. The Kuiper Belt is a ring-shaped region of the solar system extending from approximately the orbit of Neptune at 30 astronomical units to approximately 50 astronomical units from the Sun, containing billions of icy bodies left over from the solar system's formation. The Kuiper Belt is the source of the short-period comets, comets that orbit the Sun in periods of less than 200 years. The largest known Kuiper Belt objects include Pluto, Eris, Makemake, Haumea, and dozens of smaller but still substantial bodies. The Kuiper Belt is structurally shaped by the gravitational influence of Neptune, which has cleared some regions and concentrated objects in resonant orbits with the planet. Pluto, for example, is in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 of Neptune's, a relationship that stabilizes Pluto's orbit despite the fact that it crosses Neptune's orbit. The New Horizons spacecraft, which flew past Pluto in July 2015, revealed a world of unexpected complexity: nitrogen ice plains, mountain ranges of water ice up to 3,500 meters tall, possible cryovolcanism, and a surprisingly complex atmosphere. Pluto was reclassified from planet to dwarf planet by the International Astronomical Union in 2006, a decision that reflected the discovery of Eris and other Kuiper Belt objects comparable in size to Pluto. If Pluto were a planet, consistency would require including these objects as planets too, dramatically expanding the planet count. The defining criterion added to the IAU's planet definition, that a planet must have cleared the neighborhood of its orbit of other bodies, excludes Pluto, which shares its orbital neighborhood with many other Kuiper Belt objects. The reclassification generated significant popular controversy, with many people having an emotional attachment to Pluto's planetary status, but the scientific logic is sound. Pluto is simply the largest known member of a class of trans-Neptunian objects rather than a unique body meriting special classification. New Horizons revealed that Pluto has 5 moons, of which Charon is so large relative to Pluto, approximately half its diameter, that the two are sometimes described as a double dwarf planet system, with both bodies orbiting their common center of mass. There is also beauty in the small worlds that rarely get attention. Mimas, with its enormous Herschel crater, looks almost broken by one ancient impact. Iapetus has a strange two-tone surface and an equatorial ridge that makes it look unlike any other moon. Hyperion tumbles chaotically, porous and sponge-like. Pan and Atlas, small moons in Saturn's rings, were equatorial ridges of ring material and resemble tiny flying saucers. These are not major planets, but they are chapters in the same story. The irregular moons of the giant planets are especially revealing. Many orbit far from their planets, at steep inclinations, sometimes backward. They are likely captured objects or fragments from collisions. Their existence shows that giant planets did not merely form with neat families of moons. They also collected debris, lost bodies, broke bodies, and rearranged their surroundings over billions of years. A moon can be born beside a planet, captured from solar orbit, shattered in a collision, or built from a ring. Dwarf planets beyond Neptune may be geologically alive in ways no one expected. Eris is massive and distant. Haumea spins rapidly and has an elongated shape, rings, and moons. Makemake is bright and cold. Pluto has active nitrogen ice. Even small icy worlds can preserve heat, undergo differentiation, retain volatile ices, or display surface changes. The old boundary between planet and debris has become scientifically less important than the question each object asks. What has happened here, and what can this body teach us? The Oort Cloud, if it exists as models suggest, is not a belt but a vast spherical reservoir. Its objects are so far from the Sun that the gravity of passing stars and the Milky Way itself can disturb them. Most Oort Cloud bodies are small and dark, too distant to see. They are inferred from long-period comets that fall inward from all directions, as if shaken loose from an enormous halo. This makes the Oort Cloud one of the most mysterious parts of the solar system, a structure we have never seen directly, yet one whose existence explains visitors that appear suddenly in the inner sky after journeys of millions of years. A comet arriving from the Oort Cloud may have spent most of the age of the solar system in deep cold, barely warmed by the sun. Then a small gravitational nudge changes its orbit, and it begins falling inward. For millions of years it approaches, and only when it nears the sun does it awaken. Ice is sublimating into gas, dust streaming away, a coma swelling larger than planets. Something ancient and almost invisible becomes briefly spectacular, then fades back into darkness or breaks apart. Comets are among the solar system's most poetic objects because their brightness is temporary and their memory is old. The Oort Cloud is the outermost region of the solar system, a vast, roughly spherical shell of icy bodies extending from approximately 2,000 to 100,000 astronomical units from the Sun, the latter being approximately 1.5 light-years, far beyond the planetary region and already reaching into the outer darkness between stars. The Oort Cloud is thought to contain approximately 1 to 2 trillion cometary nuclei, accumulated from the original solar nebula and flung outward by gravitational interactions with the giant planets during the early solar system. The Oort Cloud has never been directly observed. No spacecraft has come remotely close to it, and individual Oort Cloud objects are too faint and too distant to detect with current telescopes. Its existence is inferred from the orbits of long-period comets, which approach from all directions and from vast distances, suggesting a source reservoir distributed in a sphere around the solar system. Occasionally, gravitational perturbations from passing stars, giant molecular clouds, or the tidal force of the galactic disk nudge Oort Cloud objects into orbits that bring them into the inner solar system as comets. Comets are among the most scientifically valuable objects in the solar system because they preserve material from the earliest stages of solar system formation, unchanged since the solar nebula condensed approximately 4.6 billion years ago. When a comet approaches the Sun and heats up, it releases gas and dust that form the characteristic bright coma and tail visible from Earth. A comet's ion tail points almost directly away from the Sun because it is shaped by the solar wind, while its dust tail can curve along the comet's orbit under the combined influence of radiation pressure and motion. The European Space Agency's Rosetta mission, which rendezvoused with Comet 67P Churyumov-Gerasimenko in 2014, provided the most detailed study of a comet nucleus in history. The mission found an extraordinarily complex and chemically rich comet, detecting over 400 different molecules in the comet's outgassing, including oxygen molecules, methane, benzene, and various organic compounds. The detection of glycine, an amino acid, in the comet's coma by the Rosetta spacecraft confirmed that the building blocks of proteins exist in comets and could have been delivered to early Earth. The solar wind is a continuous stream of charged particles, primarily protons and electrons, flowing outward from the Sun at speeds of approximately 400 to 800 kilometers per second. It extends throughout the solar system and beyond, defining a bubble called the heliosphere that separates the solar environment from the interstellar medium. The heliosphere extends to approximately 120 astronomical units from the Sun, the heliopause, where the solar wind pressure is balanced by the pressure of interstellar space. NASA's Voyager 1 spacecraft, launched in 1977, crossed the heliopause in August 2012 and is now in interstellar space, approaching the milestone of being about 1 light day from Earth in 2026, the most distant human-made object ever. The solar wind interacts with Earth's magnetic field, deflecting most particles around the planet but funneling some into the polar regions where they produce the auroras. During solar maximum, when the Sun's activity cycle peaks, powerful coronal mass ejections, clouds of magnetized plasma, can interact with Earth's magnetosphere to produce geomagnetic storms capable of disrupting satellites, power grids, and communication systems. The solar wind gives the solar system an edge, but not a hard wall. The heliopause is a boundary of pressure and particles, where the outward flow from the Sun meets the interstellar medium. Voyager 1 and Voyager 2 crossed that boundary in different directions and found that the transition was complicated. Cosmic rays changed. Plasma conditions changed. The Sun's bubble turned out to be dynamic, shaped by the motion of the solar system through the local interstellar environment. Even the edge of home is not simple. The Voyagers carry golden records, phonograph records containing sounds and images chosen to represent Earth. They are not likely to be found by anyone. Their practical purpose is almost symbolic. Yet symbolism matters. A spacecraft moving through interstellar space with greetings, music, brainwaves, footsteps, storms, and human voices aboard is a reminder that exploration is not only measurement. It is also an act of identity. It says, "This is what one small planet sent into the dark." Orbital resonance is one of the hidden musical principles of the solar system. When two bodies orbit in simple ratios, their gravitational tugs repeat in a pattern. Sometimes this stabilizes orbits, as with Pluto's 3-2 resonance with Neptune. Sometimes it pumps energy into a moon, as with the resonance among Io, Europa, and Ganymede that helps maintain tidal heating. Sometimes it clears gaps, as in Saturn's rings or the Kirkwood gaps of the asteroid belt. The solar system has no sound in space, but mathematically it contains rhythm. Lagrange points are another quiet gravitational feature. In the rotating frame of two large bodies, such as the Sun and Jupiter or the Sun and Earth, there are locations where smaller objects can remain in stable or semi-stable configurations. Jupiter's Trojan asteroids cluster near two of these points, leading and trailing the planet in its orbit. Space telescopes and solar observatories use Lagrange points near Earth because they offer stable views and efficient station keeping. Gravity does not only pull objects down or inward, it creates places, pathways, traps, and balances. The plane of the solar system is also visible from Earth as the zodiacal light, a faint triangular glow sometimes seen after sunset or before sunrise from dark skies. It comes from sunlight scattered by dust grains in the inner solar system, many of them supplied by comets and asteroid collisions. Even empty space near Earth contains dust. The planets move through a thin, luminous residue of their own system's small bodies. Exoplanets have made the solar system stranger by comparison. Before their discovery, many models assumed other planetary systems might resemble ours. Small rocky worlds inside, giant planets outside, near circular orbits, orderly spacing. Instead, astronomers found hot Jupiters skimming their stars, super-Earths with no solar system equivalent, mini Neptunes in close orbits, planets around binary stars, planets in resonant chains, planets with years shorter than Earth days, and worlds so close to their stars that rock may vaporize from their surfaces. The solar system is not the template. It is one example among many. This does not make our system less special. It makes it more specific. We have no super-Earth between Earth and Neptune. We have no hot Jupiter. Our giant planets did not migrate inward and destroy the inner rocky worlds. Our asteroid belt is low in mass. Our habitable planet has a large moon, plate tectonics, and a long-lived climate system. Whether these traits are rare or common remains unknown. But exoplanets have taught humility. Nature builds planetary systems in more ways than earlier imagination allowed. The search for life elsewhere begins at home because the solar system gives reachable examples. Mars asks whether life can begin and vanish or retreat. Europa and Enceladus ask whether life can exist in dark oceans under ice. Titan asks how far organic chemistry can go in an alien environment. Venus asks whether clouds might briefly preserve habitable niches above an inferno. The solar system is not just a collection of places. It is a set of experiments, each testing a different possibility for matter, water, energy, and time. The history of impacts also connects the planets. Craters are not simply holes. They are records of motion, violence, and survival. An impact can melt crust, excavate deep material, throw debris into space, alter atmospheres, trigger climate effects, or create hydrothermal systems in hot fractured rock. On Earth, erosion hides most ancient craters, but the Moon, Mercury, Mars, and many moons preserve them clearly. To read a cratered surface is to read a history of collisions. Earth itself was shaped by impacts after formation. Water and organics may have been delivered partly by volatile-rich asteroids or comets, though the exact contributions remain debated. The moon-forming impact reset the young Earth in many ways. Later impacts caused destruction, but may also have created environments for chemistry. The solar system's violence did not simply threaten life. Under some circumstances, it may have helped provide the ingredients and conditions from which life emerged. Planetary atmospheres are another way the solar system becomes a comparative laboratory. Mercury has almost none, only a thin exosphere of atoms knocked from the surface by sunlight and particles. Venus has a dense carbon dioxide atmosphere with sulfuric acid clouds. Earth has nitrogen, oxygen, water vapor, and life-altered chemistry. Mars has thin carbon dioxide. Jupiter and Saturn have hydrogen and helium, with traces that color their clouds. Titan has nitrogen and methane. Pluto has a thin nitrogen atmosphere that expands and contracts with distance from the Sun. Each atmosphere is a different answer to gravity, temperature, chemistry, and time. Magnetic fields vary just as strongly. Earth, Mercury, Jupiter, Saturn, Uranus, Neptune, and Ganymede have intrinsic magnetic fields, though with different strengths and geometries. Mars has crustal magnetic patches, remnants of an ancient field. Venus lacks a global intrinsic field. Uranus and Neptune have oddly tilted, offset magnetic fields, unlike the more centered fields of Earth and Jupiter. Magnetic fields reveal interiors that cannot be seen: liquid metal, conductive fluids, convection, rotation. They are invisible maps of hidden motion. The colors of the planets are not decoration. They are chemistry. Mars is red from iron oxides. Neptune is blue largely because methane absorbs red light, with haze and atmospheric structure adding complexity. Jupiter's belts are colored by compounds still not fully identified, altered by sunlight and atmospheric chemistry. Saturn's pale gold comes from hazes and ammonia clouds. Uranus has a soft cyan color. Pluto is reddish because radiation processes methane and nitrogen into complex organic tholins. Color is information written in light. The solar system also contains time capsules and ice. Water ice, carbon dioxide ice, nitrogen ice, methane ice, ammonia hydrates, and other frozen compounds behave differently depending on temperature and pressure. On Earth, ice is mostly something that melts in spring. In the outer solar system, ice can be bedrock, glacier, crust, mantle, or volcanic material. Nitrogen glaciers flow on Pluto. Water ice mountains rise on Titan and Pluto. Methane rains on Titan. Carbon dioxide freezes at Mars's poles. The word ice becomes broader and stranger the farther from the Sun one travels. Cryovolcanism, the eruption of volatile substances rather than molten rock, may occur or have occurred on several icy worlds. Instead of basalt lava, a cryovolcano might erupt water, ammonia, methane, nitrogen, or slurries of ice and brine. Possible cryovolcanic features have been discussed on Enceladus, Europa, Titan, Pluto, Ceres, and Triton. Some cases are stronger than others, and the details remain debated, but the broader lesson is clear. Geological activity does not require red-hot lava. In the cold outer solar system, frozen chemistry can behave like geology. There is a quiet human story inside the spacecraft names. Mariner, Pioneer, Viking, Voyager, Galileo, Cassini, New Horizons, Dawn, Juno, Parker Solar Probe, Perseverance, Lucy. Each mission is a tool, but also a cultural act. People built machines fragile enough to fail and strong enough to cross millions or billions of kilometers. They launched them on rockets, corrected their paths with mathematics, waited years for arrival, and received data as faint radio signals crossing space at the speed of light. The solar system we know is not only the result of telescopes. It is the result of patience. Spacecraft exploration has repeatedly humbled expectation. Before Voyager, Io was not expected to be the most volcanic world known. Before Cassini, Enceladus was not expected to be an ocean world spraying material into space. Before New Horizons, Pluto was not expected to have such a young, active surface. Before Dawn, Ceres was not expected to show bright salt deposits in such dramatic form. The pattern is almost comforting. Every time we arrive somewhere, the place becomes more interesting than the distant image suggested. This is one reason a solar system story works so well at night. The mind can travel without urgency. It can hold distances that cannot be crossed by the body. It can imagine a photon leaving the sun, a rover will pressing into Martian dust, a plume rising from Enceladus, a methane raindrop falling on Titan, a comet waking after millions of years. The scale is immense, but the details are small enough to rest on. Wonder does not have to be loud. It can be slow and precise. The planets of the solar system all orbit the sun in the same direction, counterclockwise when viewed from above the North Pole, and in approximately the same plane, called the ecliptic plane. This common orbital direction and the flatness of the planetary orbits are direct consequences of the angular momentum of the original solar nebula, which was rotating in a particular direction as it collapsed and flattened into a disk. The conservation of angular momentum as the cloud collapsed caused it to spin faster and flatten, concentrating the rotation into the disk plane. The planets formed from material in this disk and therefore inherited its rotation. The small deviations of individual planetary orbits from the ecliptic plane, orbital inclinations of a few degrees for the major planets, reflect the perturbations from gravitational interactions during and after formation. The exceptions to this orderly picture, Venus's retrograde rotation, Uranus's extreme axial tilt, and the retrograde orbit of Triton, are thought to be the results of major impacts or gravitational captures that occurred after the main phase of planet formation. The fate of the solar system is not only in the future sun, it is also in the gradual loss and rearrangement of small things. Comets will evaporate after repeated passages near the sun. Asteroids will be nudged by sunlight through the Yarkovsky effect, their orbits slowly changed by the tiny thrust of heat re-radiated from their surfaces. Moons will migrate inward or outward under tides. Rings will spread, fall, or be replenished. Planetary systems age not only through stellar evolution, but through countless small exchanges of energy and angular momentum. Long before the sun becomes a red giant, Earth's biosphere will face increasing solar luminosity. The sun brightens gradually as it ages, because helium accumulation in the core changes the balance of fusion. This slow brightening may push Earth toward a moist greenhouse state in the distant future, increasing water vapor in the atmosphere and eventually making oceans unstable. The end of habitability on Earth will likely come not from a sudden explosion, but from the patient brightening of the same star that made life possible. The giver of warmth will eventually give too much. After the red giant phase, the white dwarf sun will be small, hot at first, then cooling. The outer planets may remain, but the solar system will be transformed. Some moons may be lost. Some orbits may expand because of solar mass loss. Distant comets may be shaken loose. Future astronomers, if any exist elsewhere, might see a white dwarf with planetary remnants and infer that once there had been a main sequence star with planets around it. The solar system's story is long, but not permanent. The discovery of exoplanets, planets orbiting other stars, has transformed the understanding of the solar system's place in the cosmos. Before 1992, no confirmed exoplanet was known. By the mid-2020s, more than 6,000 had been confirmed, with thousands more candidates awaiting confirmation. The diversity of planetary systems discovered has been striking. Systems with multiple super-Earths packed into orbits closer to their star than Mercury is to our Sun, systems with hot Jupiters, giant planets in orbits of just a few days that could not have formed where they are observed and must have migrated inward from more distant formation locations and systems with architectures completely unlike our own. The solar system, by contrast, appears to have a relatively quiet history. Its giant planets are in stable, nearly circular orbits far from the Sun, creating a large region of relatively undisturbed orbital space in which the small, rocky inner planets could form and evolve without being destroyed by close encounters with migrating giants. Whether this configuration is common or unusual among planetary systems, and whether it is important for the habitability of Earth, are questions that ongoing exoplanet surveys are beginning to address. The asteroid Bennu, sampled by NASA's OSIRIS-REx mission, is a small carbon-rich world whose material returned to Earth in 2023. Samples like this are precious because they avoid the contamination and heating that meteorites can experience during atmospheric entry. Bennu contains hydrated minerals and organic compounds, helping scientists study the chemistry of the early solar system in laboratories with instruments too large and delicate to send into space. A handful of dark dust from an asteroid can carry information from the beginning of planetary history. Japan's Hayabusa and Hayabusa 2 missions also changed the way small bodies are studied. Hayabusa returned grains from the asteroid Itokawa, showing a rubble pile object made from fragments reassembled after a parent body was shattered. Hayabusa 2 returned samples from Ryugu, another primitive asteroid rich in carbon and hydrated minerals. Together with Bennu, these missions show that asteroids are not merely hazards or resources. They are messengers from the early solar nebula, carrying chemical evidence about water, organics, heating, and the building blocks of planets. Planetary defense is one of the most practical forms of solar system science. The impact that ended the age of the non-avian dinosaurs showed that small bodies can change biological history. Today, humans track near-Earth asteroids, calculate orbits, and test deflection methods. NASA's DART mission deliberately struck the small moon Dimorphos in 2022 and changed its orbit around Didymos, demonstrating that kinetic impact can alter an asteroid's path. It was the first time a species on Earth intentionally changed the motion of a natural object in space for planetary defense. The solar system is also a place of resources, though that subject requires care. Asteroids contain metals. The Moon has water ice in permanently shadowed regions. Mars has carbon dioxide and water ice that future explorers might use. But resources in space are not simple treasure waiting to be collected. They are difficult to reach, difficult to process, and embedded in environments of scientific value. The future of space use will require not only engineering but ethics. What should be preserved, what can be used, and how exploration can avoid repeating the most destructive patterns of history. Even dust has consequences. Micrometeorites fall on Earth constantly, adding thousands of tons of extraterrestrial material to our planet each year. Most are tiny, invisible to daily life, but together they represent a continual exchange between Earth and the rest of the solar system. Some dust comes from comets, some from asteroid collisions. When Earth passes through streams of comet debris, we see meteor showers, brief lines of light made by grains no larger than sand burning in the upper atmosphere. A meteor shower is a planet moving through the memory of a comet. The zodiac names attached to the ecliptic are ancient cultural overlays on a physical fact. The planets all remain near the same path in the sky because they share the plane of the solar system. Ancient observers did not know about the flattened solar nebula, angular momentum, or planetary accretion, but they noticed the path. The sky preserved the geometry before science explained it. In this way, the solar system has always been partly visible to patient attention. The search for Planet 9 is another reminder that the solar system may still contain surprises. Some distant Kuiper Belt orbits have been interpreted by some researchers as possible evidence for an undiscovered massive planet far beyond Neptune, while others argue the pattern may arise from observational bias or other dynamical effects. No such planet has been observed. The idea remains intriguing but unconfirmed. A good solar system story should leave room for uncertainty without turning uncertainty into a claim. Sometimes the honest sentence is, we do not know yet. The inner planets also preserve different answers to the question of plate tectonics. Earth has active plate tectonics, which recycles crust and regulates climate over long timescales. Venus may have a different style of crustal recycling, perhaps episodic or localized rather than Earth-like plates. Mars appears to have had early volcanism and tectonic stresses, but no present global plate tectonic system. Mercury shrank as it cooled. The rocky planets are variations on heat loss. Their surfaces show how interiors cool, contract, crack, erupt, and sometimes recycle. Water is a connecting theme across almost every part of the solar system. Earth has surface oceans. Mars had ancient lakes and rivers, and still has ice. Mercury has polar ice and shadow. The Moon has polar volatiles. Ceres has hydrated minerals and salts. Europa, Ganymede, Callisto, and Enceladus likely have hidden oceans. Titan may have an internal ocean beneath hydrocarbon weather. Pluto may have had, or may still have a subsurface ocean. Water is not rare in the solar system. Liquid surface water at Earth-like conditions is rare, but water itself is woven through worlds. Life, however, remains known only here. That fact should make the solar system feel not empty, but profound. We have found ingredients, environments, energy sources, oceans, organics, and histories that could matter for biology. But we have not found a second living world. This keeps astrobiology in a state of disciplined wonder. The solar system gives reasons to search, but not permission to assume. Every mission to Mars, Europa, Enceladus, Titan, or Venus is part of a careful question. Did life happen twice? Or is Earth, so far, the only place where chemistry crossed that threshold? The scale of spacecraft communication adds another quiet dimension. A command sent to Mars takes minutes to arrive, depending on the planet's positions. A signal from Saturn takes more than an hour. A signal from Voyager 1 now takes almost a full day to reach Earth one way, and a reply would take nearly as long to return. Exploration in the outer solar system is therefore not immediate control, but delayed conversation. A spacecraft is given instructions, performs them far away, and answers later. The farther we go, the more exploration resembles trust. The sun's gravity holds the system, but light reveals it. Telescopes collect reflected sunlight from planets, thermal radiation from warm surfaces, radio emissions from magnetic fields, and spectra that expose atmospheric gases. A spectrum can tell us whether a world has methane, carbon dioxide, sodium, water vapor, or haze. It can reveal temperature, composition, and motion. The solar system is read through light divided into colors, through shadows crossing surfaces, through radio signals bent by atmospheres, through tiny changes in spacecraft velocity. Seeing, in planetary science, often means measuring what light has carried. There is something peaceful about the fact that the planets do not need to be seen in order to continue. Neptune moves through its long orbit whether anyone observes it. Titan's methane lakes darken under orange haze. Europa's ice cracks. Mars gathers frost at its poles. Dust falls into Saturn's rings. The sun fuses hydrogen. The Oort Cloud waits. Human attention is new here and brief. The solar system existed almost its entire life without witnesses who could name it, and yet naming it is one of the ways we belong to it. A child learning the order of the planets is taking part in a tradition much older than spacecraft. First comes the simple list: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Later the list opens. Mercury has ice. Venus has a runaway greenhouse. Earth has a biosphere. Mars has dried rivers. Jupiter has ocean moons. Saturn has rings and plumes. Uranus is sideways. Neptune was predicted. Pluto is a dwarf planet with glaciers of nitrogen. The simple list becomes a map of wonder, and the map never stops growing. The quiet science of the solar system is partly the science of comparison. Why did Venus lose its habitability while Earth kept oceans? Why did Mars cool and dry? Why did Jupiter become enormous and Mercury remain small? Why do some moons have oceans and others preserve ancient craters? Why are some worlds active and others still? Every answer leads into formation, chemistry, gravity, heat, distance, impacts, and time. The solar system teaches through differences. It also teaches through continuity. The same gravity shapes a falling apple, the moon's orbit, Jupiter's moons, Saturn's rings, and comet paths from the Oort Cloud. The same physics of heat and pressure changes rock, ice, atmosphere, and plasma. The same chemistry forms water on Earth, ice on Europa, vapor in comet tails, and hydroxyl in lunar soil. The solar system is varied, but it is not random. It is one physical story told in many materials. When we say home, we usually mean a room, a house, a town, a country, or a planet. But there is a larger home around that home. The region of space, shaped by the Sun Earth, is not isolated. It is one orbit in a family of orbits, one atmosphere under a star, one biosphere inside a heliosphere. The solar system is the environment of Earth at the grandest local scale. It is the neighborhood that made our world possible and the first wilderness beyond it. And so the solar system can be calming not because it is small or safe, but because it is ordered enough to trust. The planets return. The moon changes phase and returns. Mars brightens and dims. Jupiter rises. Saturn follows. Comets appear and leave. The cycles are not perfect circles, and the system is not eternal, but it is steady on a scale far beyond a human day. To think about it at night is to place one's own moment inside a larger rhythm. The naming of worlds is another quiet human layer placed on top of astronomy. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune carry names from Roman and Greek mythology, inherited through centuries of European astronomical tradition. Their moons carry other systems of names. Shakespeare and Pope around Uranus, sea deities around Neptune, giants and lovers around Jupiter, titans and figures from many mythologies around Saturn. The names are not the objects themselves, of course, but they are part of how human memory attaches to distance. A moon becomes easier to imagine when it has a name, and a name becomes a small bridge across millions or billions of kilometers. Time on other worlds also stretches the imagination. A year on Mercury lasts 88 Earth days. A year on Neptune lasts about 165 Earth years. A day on Jupiter lasts less than 10 hours, while a rotation of Venus takes longer than its year. Seasons on Uranus last decades. A human lifetime would be less than half of a Neptunian year, while on Mercury a person would see hundreds of birthdays. Time is not one universal human rhythm imposed on the solar system. Each world has its own clock, made from rotation, orbit, tilt, and sunlight. Gravity changes ordinary experience just as completely. On Mars, a person would weigh about 38% of their Earth weight. On the Moon, about 1/6. On Jupiter, if there were a surface to stand on at a comparable pressure level, the gravitational pull would be more than twice Earth's. On small asteroids, gravity can be so weak that a jump could send a person drifting dangerously high. Gravity shapes mountains, atmospheres, human motion, ocean tides, and whether a body can become round. It is the quiet sculptor of worlds. Escape velocity is one way to feel the difference between worlds. A small moon loses gases easily because molecules moving fast enough can escape its weak gravity. A massive planet holds an atmosphere more tightly. This is why Titan, larger than Mercury's moon like companions and cold enough to slow gas molecules, can maintain a thick atmosphere, while Earth's moon cannot. Atmospheres are not simply acquired. They are kept or lost through gravity, temperature, chemistry, magnetic environment, impacts, and geological supply. Every atmosphere is a history of retention and loss. The habitability of a world is therefore never just one number. Distance from the sun matters, but so do atmospheric pressure, greenhouse gases, geological recycling, water inventory, stellar activity, magnetic shielding, rotation, clouds, surface chemistry, and time. A planet can be inside a habitable zone and still be sterile, or outside the classical habitable zone and still contain a subsurface ocean. The phrase habitable zone is useful, but the solar system teaches that habitability is multidimensional. Life requires conditions, but planets provide conditions in complicated ways. The chemistry of sunlight also changes with distance. Near Mercury, sunlight is intense, nearly 7 times stronger than at Earth on average. At Mars, it is less than half as strong. At Jupiter, it is about 4% of Earth's. At Saturn, about 1%. At Neptune, sunlight is roughly 900 times weaker than at Earth, and the sun would look more like a brilliant star than a warm disk. Yet even there, the sun still matters. It lights Neptune's clouds, warms Triton's nitrogen frost, and marks the center around which all these cold worlds continue to move. The solar system contains a record of migration. The giant planets likely did not remain exactly where they formed. Models suggest that interactions with planetesimals caused their orbits to shift, rearranging small bodies and shaping the Kuiper Belt, asteroid belt, and impact history of the inner planets. Planetary migration sounds dramatic, but it can occur slowly through countless gravitational exchanges. A planet throws a small body inward and moves slightly outward, or throws it outward and moves slightly inward. Across millions of encounters, the architecture changes. Resonance can protect and destroy. Pluto survives crossing Neptune's orbital distance because its resonance means the two bodies are never in the same place at the same time. But resonances in the asteroid belt can remove objects, increasing their eccentricities until they encounter Mars or Jupiter and leave the belt. The same mathematical principle can create stability in one place and instability in another. In the solar system, a simple ratio can be a shelter or a doorway. There are also Trojan populations, objects that share a planet's orbit near stable Lagrange points. Jupiter has thousands of known Trojans, and NASA's Lucy mission is visiting several of them to study material left from the early solar system. Neptune has Trojans too, and even Earth has a small number. These bodies are not moons because they do not orbit the planets directly. They orbit the sun in step with a planet, held in gravitational balance. They are companions, but of a different kind. The sun itself moves. The solar system does not sit still in the galaxy. It orbits the center of the Milky Way roughly every 225 to 250 million years, carrying the planets through the galactic disk. Since Earth formed, the solar system has completed perhaps 20 galactic orbits. The dinosaurs lived on a planet located elsewhere in the galaxy. The first forests grew under the same sun, but the whole system was in a different part of the Milky Way. Home is moving, even when night feels still. The solar system's plane is tilted relative to the plane of the Milky Way. So from Earth, the Milky Way and the path of the planets cross the sky at angles that change with season and latitude. Ancient sky watchers saw patterns, but not the full geometry. Modern astronomy reveals that we live inside overlapping planes: the horizon of Earth, the equator of Earth, the ecliptic of the solar system, and the disk of the galaxy. The sky is not flat. It is a set of coordinate systems made visible by time. Even the smallest moons can tell stories about formation. Phobos, the inner moon of Mars, is so close to the planet that it rises in the west and sets in the east, crossing the Martian sky quickly. It is slowly spiraling inward and will eventually be torn apart or collide with Mars. Deimos, farther out, moves more slowly. Whether these moons are captured asteroids or formed from impact debris remains debated. Mars, small and quiet, still keeps two mysterious companions. The shapes of small bodies reveal their weakness. Large planets are round because gravity overwhelms the strength of rock and ice, pulling matter toward hydrostatic equilibrium. Smaller asteroids and moons can keep irregular forms because their material strength resists gravity. This is why Ceres is round while many smaller asteroids are potato-shaped. Roundness is not aesthetic. It is a sign that gravity has become strong enough to make a body yield. Temperature also shapes geology in unexpected ways. On Earth, water is the fluid that erodes, transports, freezes, and melts in ordinary weather. On Titan, methane and ethane fill that role at far colder temperatures. On Pluto, nitrogen ice can flow like a glacier. On Io, sulfur and silicate lava erupt under tidal heating. On Venus, rock sits near the temperature at which some metals would soften. Each world has its own material behavior because the same substances enter different regimes under different pressure and temperature conditions. The phrase ingredients for life can sound simple, but it includes many levels. Water is a solvent. Carbon chemistry provides flexible molecules. Energy drives reactions away from equilibrium. Stable environments allow complexity to persist long enough to evolve. Interfaces, such as mineral surfaces, ice boundaries, pores in rock, or hydrothermal vent systems, can concentrate molecules and create gradients. The solar system contains many ingredients in many places, but the recipe for life remains unknown. That unknown is not a weakness in the story. It is one of the reasons the story continues. The search for life must also protect the worlds it studies. Planetary protection protocols are designed to prevent spacecraft from carrying Earth microbes to places where they could contaminate potential ecosystems or confuse future science. They also protect Earth from returned samples, even when the risk is judged very low. Exploration is therefore not simply reaching a place. It is reaching carefully. The more interesting a world is for life, the more responsibility it demands. A future sample from Mars, if returned successfully, could be one of the most important scientific materials ever studied. It might contain no evidence of life, and that would still matter because it would constrain the conditions under which life does or does not emerge. It might contain chemical patterns suggesting ancient biology, which would require extraordinary caution and confirmation. It might deepen the mystery. In science, a sample is not only valuable when it gives the desired answer, it is valuable when it gives a reliable answer. The same is true of Europa or Enceladus. A mission may find an ocean chemistry rich with energy and organics, but no life. That would be profound. It would suggest that ingredients are not enough, or that life is harder to start than hoped. Or a mission might one day find convincing signs of biology, and everything about humanity's place in nature would change. The solar system holds both possibilities quietly, without resolving them for us yet. The wonder of the solar system is therefore not only in spectacular images. It is in the discipline of not knowing too quickly. Scientists can say that Enceladus has organics without saying it has life. They can say that Venus has chemistry worth studying without saying microbes float there. They can say that Mars was once habitable without saying it was inhabited. This careful language is part of what makes the subject beautiful. Real wonder does not require exaggeration. One could imagine the solar system as a set of rooms around one lamp. Mercury is the scorched stone room nearest the flame. Venus is the locked greenhouse. Earth is the blue room full of weather and breath. Mars is the cold red room where rivers once ran. The asteroid belt is the unfinished workshop. Jupiter is the great storm hall with ocean moons circling it. Saturn is the ringed chamber. Uranus is the tilted blue room. Neptune is the windy dark room. Beyond them are the frozen archives. All belong to the same house of the sun. And in that house, Earth is not the largest, not the oldest, not the most massive, not the most dramatic. It is simply the known living room, the one place where the solar system has become aware of itself through organisms able to look outward and ask what surrounds them. That is not a scientific measurement, but it is a truthful perspective. The atoms of Earth arrange themselves into eyes, telescopes, rockets, spectrometers, and questions. The solar system is not only something we observe, it is something that, in us, has begun to observe. This thought can be held gently, without grandiosity. A person lying in a quiet room at night is made from solar system material. Calcium, carbon, oxygen, iron, sodium, potassium, all gathered from Earth, which gathered them from the solar nebula, which gathered them from older stars. The body is local geology made temporary and alive. Breathing is atmospheric chemistry. Thinking is planetary matter becoming aware for a little while. The solar system is not far away. It is also here, in every cell that depends on the sun's old light. There is another quiet scale inside the solar system, the scale of radio time. Light from the sun reaches Earth in about 8 minutes, Mars in roughly 3 to 22 minutes, depending on orbital positions, Jupiter in more than half an hour, Saturn in over an hour, and Neptune in about 4 hours. A spacecraft at Neptune cannot be driven like a remote-controlled toy. It must be trusted with instructions. The farther a mission travels, the more planning must happen in advance, and the more every success depends on engineering that can survive without immediate help. Spacecraft also use the planets themselves as engines. A gravity assist can steal or give a tiny amount of orbital energy from a planet, changing a spacecraft's speed and direction without spending much fuel. Voyager used this principle to visit the outer planets. Galileo, Cassini, Juno, and New Horizons used planetary flybys to bend their paths. Gravity assists are elegant because they turn motion into opportunity. A planet moving around the sun becomes, for a passing spacecraft, a way to reach somewhere that would otherwise be impossible. The solar system is not cleanly divided into science and poetry. A shadow crossing Jupiter is both an orbital event and a beautiful sight. A crater count on the moon is both a dating method and a record of ancient violence. A spectrum of Titan is both chemical data and a glimpse of orange haze over alien rivers. A rover wheel track on Mars is both engineering and a mark made by Earth on another world. The emotional response does not weaken the science. When held carefully, it can keep attention awake long enough for understanding to deepen. Our own daily life is still synchronized with the solar system. The day comes from Earth's rotation. The month comes from the moon, even if modern calendars only partly remember it. The year comes from Earth's orbit. Seasons come from axial tilt. Tides come from the moon and sun day. Even the week, though cultural rather than physical in the same way, carries ancient planetary names in many languages. We do not merely live under astronomical cycles. We organize ordinary time around them. Perhaps that is why the solar system feels both immense and familiar. Its distances exceed imagination, but its rhythms are built into sleep, weather, calendars, tides, farming, migration, navigation, and memory. The planets are far away, yet the structure they belong to has always shaped life here. To learn the solar system is not to leave home completely. It is to discover the larger shape of the home we were already inside. There is also comfort in remembering that knowledge of the solar system has grown by correction. Old maps changed. Pluto changed category. Mars changed from a world of imagined canals to a world of ancient rivers. Venus changed from a possible tropical planet to a greenhouse warning. The moon changed from a distant light to a place with footprints and samples. Science does not make the solar system smaller by explaining it. It makes it more precise and often more mysterious. Every new measurement turns a simple object into a world. A point of light becomes weather, chemistry, interior structure, orbit, history, and future. That is the quiet magic of planetary science. It teaches the mind to look longer. The longer one looks, the less empty space becomes. Another reason the solar system holds attention is that every world preserves a different kind of memory. Mercury preserves the memory of impact and contraction. Venus preserves the memory of climate pushed into runaway heat. Earth preserves oceans, plate tectonics, weather, and life. The moon preserves ancient craters because it has almost no atmosphere and no rain to erase them. Mars preserves rivers that no longer flow. The giant planets preserve the chemistry of the early nebula in enormous atmospheres of hydrogen and helium. The icy moons preserve oceans under shells, and the small bodies preserve primitive minerals almost unchanged from the beginning. A tour of the solar system is therefore not only a tour through space. It is a tour through different ways of keeping time. The frost line, sometimes called the snow line, is one of the quiet boundaries that shaped everything. In the young solar nebula, close to the forming sun, it was too warm for water and many other volatile compounds to freeze into solid grains. Farther out, ices could survive and become part of growing bodies. This is one reason the inner planets are small and rocky, while the outer planets became large worlds surrounded by icy moons and volatile-rich debris. The line was not perfectly fixed, and the early disk was dynamic, but the idea matters because temperature sorted the ingredients of planets before the planets fully existed. Chemistry became geography. Distance from the sun helped decide whether a world would be built mainly from metal and rock, or from rock, ice, gas, and frozen volatiles. The small moons of the giant planets make that history more complicated. Some probably formed in disks around their planets, like miniature versions of the solar nebula. Others were captured later, arriving as asteroids or Kuiper Belt objects and becoming irregular moons with tilted, stretched, or backward orbits. These captured moons are like fossils of old encounters. They tell us that the solar system was not always as calm as it now appears in a school diagram. Bodies passed close to planets. Orbits changed. Some objects were ejected. Some were broken apart. Some were caught and kept. Every irregular moon is a small reminder that gravity does not only arrange. It also edits, steals, scatters, and preserves. The surfaces of airless worlds are also changed by space itself. Without an atmosphere, a surface is exposed to micrometeorites, solar wind, cosmic rays, and extreme temperature swings. Tiny impacts slowly grind rock into regolith. Charged particles alter surface chemistry. Ice exposed to radiation can darken, break apart, or create new molecules. This process, called space weathering, means that a moon or asteroid surface is not simply a frozen snapshot. It is being worked on constantly by the environment around it. The change is slow, but over millions of years, slow processes become powerful. A gray lunar plain, a reddened asteroid, or a darkened icy surface may carry the signature of countless small interactions with space. The solar system also teaches that atmosphere is destiny, but not destiny in a simple way. Mercury has almost none and suffers wild temperature swings. Venus has too much greenhouse atmosphere and becomes hotter than any other planet. Mars has too little and loses stable surface water. Earth has enough pressure, enough greenhouse warming, enough magnetic and geological support, and enough water cycling to remain habitable for a long stretch of time. Titan has a thick nitrogen atmosphere far from the Sun, where methane plays a role somewhat like water does on Earth. Pluto, tiny and distant, has a thin atmosphere that changes with its long seasons. Atmospheres are not just blankets. They are active chemical, thermal, and geological systems. Even the absence of life elsewhere so far is informative. If Mars once had lakes and rivers, but no life, that would tell us something profound about how difficult abiogenesis may be. If Mars had life and lost it, that would tell a different story, that biology can begin but not always endure. If Europa or Enceladus contains life and darkness, it would show that sunlight is not required for a living world. If they contain only chemistry, that would also matter, because it would reveal how far complex chemistry can travel without crossing into biology. Science does not need every answer to be exciting. Sometimes the absence of a result is a result with a shape. The robotic exploration of the solar system is also an experiment in patience. A spacecraft may spend years crossing empty space before one brief encounter. New Horizons traveled nearly a decade before Pluto became more than a point. Cassini took 7 years to reach Saturn and then spent 13 more years orbiting among rings and moons. Europa Clipper will make repeated flybys rather than orbit Europa directly because Jupiter's radiation environment is so harsh. Dragonfly is planned to move across Titan by flying through its dense atmosphere. Each mission is shaped by the world it visits. Engineering becomes a conversation with gravity, radiation, sunlight, cold, distance, and time. The more we explore, the more the word world expands. A world does not have to be Earth-sized. It does not have to have blue skies, open oceans, or a breathable atmosphere. Io is a world of volcanoes. Europa is a world of ice above water. Titan is a world of methane weather. Ceres is a world of salt deposits and ancient brines. Pluto is a world of nitrogen glaciers and mountains of water ice. Bennu and Ryugu are tiny worlds, but they contain chemistry older than Earth. The solar system teaches that a world is any place with history, structure, change, and a way of being itself. There is also a quiet humility in the fact that many of the most interesting places are not the most obvious ones. The biggest planets are spectacular, but their small moons may be more important in the search for life. Pluto was demoted in category but promoted in wonder when New Horizons revealed its active surface. Ceres was once an asteroid, then a dwarf planet, and now a clue to water-rich chemistry in the inner solar system. Enceladus was a small, icy moon before Cassini saw its plumes. Classification helps science organize, but exploration often makes every category feel too small for the thing itself. The solar system's beauty comes partly from contrast. There is fire at the Sun, sulfur volcanoes on Io, acid clouds on Venus, dust on Mars, water ice at Mercury's poles, methane rain on Titan, nitrogen geysers on Triton, rings around Saturn, and faint dust glowing before dawn as zodiacal light. The same laws of physics produce all of this, not by changing rules, but by changing conditions, distance, mass, temperature, chemistry, impact history, and time. A calm voice can move from one world to the next because the variety does not need to be forced. It is already there. And perhaps that is why this subject can carry a listener through a long night. The solar system gives the mind many doors, but all of them open into the same house. A person can rest for a while with Mercury's shadowed craters, then drift to the clouds of Venus, then to the blue curve of Earth, the dusty valleys of Mars, the storms of Jupiter, the rings of Saturn, the sideways light of Uranus, the dark winds of Neptune, the nitrogen plains of Pluto, and finally the long cold patience of the Oort Cloud. Each place is separate, but none is isolated. gravity holds the whole story together. The total surface area of all the planets in the solar system, if spread flat, would cover approximately 25 billion square kilometers, roughly 50 times the total surface area of Earth. But this comparison understates the scale of the solar system. The volume of the solar system inside Neptune's orbit is so vast that the planets and moons, combined, constitute a tiny fraction of the total space. The solar system is mostly empty, with the planets and other bodies separated by distances so large that a journey between them, even at spacecraft speeds, takes months to years. The Voyager 1 spacecraft, traveling at approximately 17 kilometers per second, one of the fastest human-made objects relative to the Sun, would take approximately 17,000 years to reach the nearest star even if it were headed in that direction, which it is not. The solar system is not only vast by human standards, but small by astronomical standards, just one of hundreds of billions of planetary systems in the Milky Way, orbiting just one of the approximately 300 billion stars in our galaxy, in a universe containing approximately 2 trillion galaxies. And yet from here, from this small planet in the outer arm of an ordinary galaxy, we have sent machines to every planet in our solar system, landed on the Moon and on Mars, orbited comets, sampled asteroid surfaces, and sent 2 spacecraft out of the solar system entirely into interstellar space. In the span of approximately 6 decades, a blink in astronomical time, humanity has gone from being confined to the surface of one small world to having physical representatives in interstellar space. The solar system is large, and mostly cold, and mostly empty, and almost entirely dark beyond the small warm circle of the sun's light. It has been turning quietly for 4.5 billion years, and it will continue to turn for billions more, long after the particular arrangement of chemistry and biology on one of its small worlds has run its full course. It is, by any measure, an extraordinary place to be. Sleep well. Good night.